Gentlemen, welcome back to the shop. Today we're going to take a look at how we test one of these guys. This is a 5 kV medium voltage vacuum circuit breaker. Every breaker is a little bit different. The Eaton's different than the ABB's, different than the Square D's, different than the Siemens. But for the most part, they're all going to be fairly, the steps that we take to test them are going to be pretty much identical, with a few little caveats here and there. Obviously, big breakers out in a substation switch yard are going to have a few more things that we're going to take a look at. I'm sure I'm going to make a different video in the future with all of the optional tests that we're not going to look at today, but I just want to do sort of a primer on getting started, the equipment that you're going to need, how to do it safely, what all the different settings and the nomenclature and all that means. Get you guys a sort of a basic idea of what testing a medium voltage vacuum circuit breaker looks like. We're going to go off the NETA 2019 MTS, Maintenance Testing Standard. So they publish all the tests that need to be performed on a breaker like this. The handful of them that are required, obviously we have to do the visual mechanical inspection. Look at it. Is it on fire? No, it's probably good. How does it look? Is there any dirt, water, signs of arcing, pitting, things like that? Does it mechanically operate? Can we manually charge, trip, close? We have to do the electrical operation. So if it has a charging motor, it has to work. So we're going to electrically charge it. We're going to electrically trip and close. We're going to make sure if it's in the cell, here I've got one on a pallet, but if it's in the cell, we have to make sure that it operates from every trip device. So every relay, every SCADA, DCS input that can open and close this breaker. We need to verify that those work with the breaker racked into the test position. Clean and lubricate. I'll show you where the lubrication points are. That's really important. The electrical tests that have to be performed per NETA MTS on this breaker is it has to be measured, insulation resistance on DC. We're going to high pot per the manufacturer's published data. The operations and maintenance manual will tell you what values to high pot it at. We are going to perform the contact resistance test or the ductor test with the vacuum balls closed. The last one, and the kind of tricky one that we have to do, is the contact timing test. So all 3 poles have to close at exactly the same time within a specified period. There's a couple other little minute things that we'll get into. Let's go ahead and get started. All right, one of the first things that I want to do is take the cover off the breaker because we have to inspect the internal mechanism for lubrication points. Obviously, evidence of damage, ingress of water, ingress of rodents, arcing, tracking, things like that we want to take a look at. We're going to pull our cover off. Nameplate's right there on the cover. That tells you everything you need to know about the breaker. Serial number, the trip and close voltage, stuff like that. Let's take a quick tour of the inside of one of these breakers. Lighting is a little bit weird. We've got our trip and close springs. So those are what store the energy. That's that guy and that guy. That's what store the energy to obviously trip and close the breaker. That's how it operates so quickly. There is a charging motor. We want to make sure that there's a decent amount, a thin film of grease on the gears out of the charging motor. This bar across the bottom is actually what moves the physical contacts themselves. So if we can see these little, focus, there we go. If we see these little bars coming out the bottom off of this bar will rock back and forth, and that's all the motion that it takes to open and close the contacts on the breaker. So we've got our A phase is actually over here. See if I can get this in focus here. There we go. So it's actually two little bars that come off this main drive rod here. And when the breaker operates, when it closes, that's that same rod. That is that same rod that comes out the front for each phase. Got one on the other phase as well. and those push this whole assembly up. This is the vacuum bottle in the back. Let me get that in focus there. That's the vacuum bottle. The contacts in there only move, I mean, a couple thousandths of an inch, like not a whole lot. That rod doesn't have to move very much in order for the contacts to open or close. These are the primary disconnects. That is when you rack the breaker into the cell. That's how the cell mates with the breaker, or rather the breaker mates with the cell. And these down here are our secondary disconnect pins. So that is how control signals and status signals out of the breaker are sent back to the control stuff in the cell. One thing you'll notice as we look around inside here, there's not really any electrical controls. There's a couple. We've got some aux contact switches in here, which obviously connect to the secondaries on the back, that this physical thing rotates when this main operate rod rocks back and forth. This is what tells the external control circuits out in the cell or in the switchgear somewhere where this is connected to. This is what tells everything else whether the breaker is open or closed. This is our Y relay. So this is our, some breakers are called the anti-pump relay. This is what prevents the breaker from going open, close, open, close, open, close over and over and over again. But realistically, okay, so we've got a couple coils. We've got the trip and the close coil are in here somewhere. Doesn't really matter which one's which. We've got a couple more status contacts, but you'll notice, very dissimilar to all of the low voltage circuit breakers, there's no protection. There's nothing that tells it when to trip. This is how it physically trips. Voltage is applied across the coil and it physically opens or closes. But there's no control. There's no overcurrent element. This doesn't even have CTs in it. The CTs are going to be located in the cell, and so is the protection. For medium voltage equipment, the overcurrent device is going to be a relay located somewhere in the switchgear. It's not in the breaker. So we have to make sure that the breaker operates well by itself independently. It's a completely separate external thing to test the relays, the protection devices. What we're doing here is we're just testing the breaker. We're gonna manually close this. So we need to run the charging handle. And you're gonna charge and charge and charge until it makes a loud, satisfying click. We are open and charged. So with the breaker charged and open, we can go closed and open. And that's our manual test. We've used the push buttons to make it operate manually. So the next thing that I want to do, I'm lazy. I don't want to manually charge this again for the million times that I have to do this. What I'm going to do is I'm going to hook up a power supply and do it automatically. Okay, don't mind my super sketchy test set. This is a home-built 120 volt DC power supply. Works a treat. Obviously we're hooking up onto the secondary block. So this is where the controls from the cell would come in, and we're connected straight to the pins. There's definitely better ways to do this. If you had a female section of the secondary block out of a switchgear or a test umbilical, that would be a lot better. I don't have one since we're doing this in the shop, so this is what we got. So this breaker runs on 125 volt DC for the charging motor, the trip, and the close. So we're going to operate that with this 120 volt DC power supply. That's going to be different depending on, some run on AC charging motors and DC controls. Some have AC charge and close, but a DC trip coil. So just verify what you actually need for your breaker. This is going to be different for each of them. Again, read the manual for your breaker and it'll have all this information in it. So we're going to turn this on and see what happens. It should charge and do nothing else. A little noisy. The click at the end says it's all the way charged, just like we had when we were manually charging it. Goes all the way charged, and then a limit switch, when it is charged, opens up the charge circuit. So we can actually leave this on and go about the rest of our work. And then whenever we need to close and open it, that'll have it charged and ready for us without having to manually pump it. All right, pardon the terrible framing. I lost my tripod. So with the charging motor connected, we can go closed. It'll start charging automatically. So we're closed and charged. This is what would normally happen in the cell. If we go open, stays charged, I can close it. Charging motor will continue to run. All right, so next up here, we're gonna run the breaker timing test. It's kind of a pain in the butt to hook up, especially on a breaker like this. This test set was definitely more geared towards bigger breakers. The hookup on this, when we're going straight to the secondary stabs, it's not easy. It's not easy to hook up. So I've got my drawing, which is not going to be exposed right or in focus. We've got the manual open with the pinout of the secondary. We're going to reference this, and then we're also going to reference the drawing from the manual from our test set, because that is going to tell us how the test set needs to cut in between the open and closed circuits. So every test set is going to be different, every breaker is going to be different, but this should show you vaguely how to hook it up, and you just sort of have to interpret how to combine those things. I might put a graphic up on the screen here-ish with how I'm connected to this one where it combines the two. What we really need to do is come up with a drawing of what this is trying to do and what the breaker wants connected to it. We can let the charging motor run, we close the breaker and have the test set tell it to close and time it. And then we tell the test set to trip the breaker and record the time that it takes to trip. I figure this part's not going to be super interesting for you guys unless you know what I'm doing. So on this test set, you can actually run it from your laptop by plugging it in on USB. That works great. We're not going to do that because we're lazy. We're going to go time breaker. Do we have a resistor? There is no resistor needed for this breaker. We're just going to go dry contacts, 120 volts or 125 DC straight into the trip and close motor. So we're going to go no. Timing window, 1 second's fine, doesn't really matter. Internal trigger or external trigger. So I want my test set, these wires here that go to the aux block or the secondary contact block, I want the test set to control when it tells the breaker to open and close. So we're gonna go internal trigger, it's option 1. And we are open or closed right now. We're charged and closed. So we're gonna do the trip first, which is open, option 1. And now this is gonna be really tricky getting this in frame. I need to, per what this thing says, I need to hold the arm button and hit start at the same time. Hold the arm button, hit start. There we go. All right, now pulling the results off of here, unless you're doing it on the software, obviously I'm showing you the quick and dirty way. We're gonna go get results, print test results, and then this has a printer on it, like a thermal paper printer, which I don't know why you would use, probably a holdover from an older test set. We're just gonna click display results and then scroll up until we find our result. There we go, that's our timing. So this operated in less than 2 cycles for all 3 poles. Click time breaker, continue, don't save. Insertion resistor, no. Windows 1 second, doesn't really matter. Internal trigger, and then we're gonna go close. And now this is telling me I have to, again, hold arm and click start. Hold arm, click start. Which should be get results. Because we're doing 1 test at a time. You can set this up to do a bunch of them, but we're only gonna do 1 test at a time. This one operated in about 3 cycles, so 50 milliseconds, and 52.05. So that's right on the cusp of being in tolerance. All right, this is a 5 kV breaker. So we're gonna test all of the insulation resistance tests we're gonna do with a 5 kV megger set to the 2.5 kV range. We're gonna do 3 distinct tests. Well, it's actually like 9 tests, but we're gonna do 3 different setups. So the breaker's closed right now. I've got it closed. We're gonna do, with the breaker closed, we're gonna do A phase to ground, B phase to ground, C phase to ground. We're gonna do that for 1 minute. And then we're gonna do, with it still closed, A phase, B phase, C phase, and then A phase to C phase. So we're gonna do each phase to the chassis, essentially. Each phase to the other phases, and then we're gonna open the breaker and we're gonna megger across the vacuum bottle. So we're gonna do that, each test for 1 minute, winds up being 9 total minutes of test. So just like that, we've got our megger set to 2500 volts. We're gonna do that 3 times, A phase ground, B phase ground, C phase ground. And then we're gonna do A to B, A to C, B to C, and then we'll open it and go across the vacuum bottles. And I'm gonna speed this part up because it's boring. All right, I don't know how well y'all are gonna be able to see this. These test sets have a couple different modes. This is the Megger DLRO 10 HD. I'm gonna set this to auto, which as soon as these make contact, it starts pushing current. We're on the 10 amp range. Obviously we're looking for the lowest amount of resistance possible because I'm expecting these contacts to be in a really good condition. Per the manual, they should be below 50 micro ohms. So yeah, start pushing some current through and see what we get. One thing that I like to do when I start testing is just make sure I do an idiot check. I make sure I'm not an idiot, make sure I have everything hooked up right. So we're gonna do try and get this so we can both see it here. That makes it almost impossible. I try to make it so that we can verify that our test leads work. So I'll go on a single piece of copper. And this says I got 2.9 micro ohms. So the lead resistance essentially is 2.9 micro ohms. So I know that my leads are good. That's a tiny, tiny amount of resistance, like millionths of an ohm. So we're gonna go from a consistent spot on all 3 phases. Looking good. This one's 28.6 micro, which is below 50, which should be good. 25.0, looking good. All right, and 19.7. So very similar to our low voltage circuit breaker tests. We need to have all 3 measurements within 50% of each other. So the easy way to do that is you start with your lowest value, multiply that by 1.5. So our lowest was like 19.7. So as long as the other 2 readings are below 30, just in my head, I know, hey, it passes on ductor. So all 3 phases were within 50%. We're good to go. All right, what's up next? All right, one thing that a lot of guys seem to miss, I honestly sometimes forget as well, but with the breaker in the closed position, and this is gonna be different between breaker manufacturers, we need to measure the critical distances. Now on this Square D VR breaker, they tell us that the critical distance with the breaker in the closed position, so we're in the closed position right now, I need to measure this tiny little gap right here, and they call that my E gap. So we're gonna measure that on our calipers, go ahead and zero these out. And we're gonna get in here nice and friendly like. You want the calipers to be as square with what you're measuring as possible, but that's almost impossible here. Oh God. Okay. Oh, I bumped it. Fudge. Yeah, start a YouTube channel. It'll be fun, they said. Just record yourself fucking up in the shop all day. All right, so we got that set. Measurement is 0.14 inches. That was miserable to get. We're within tolerance. you would do the same thing on B and C phase. I've already done that, so we are good to go. Okay, so for this setup, we're doing high pot, which is a vacuum bottle integrity test. Really the best way, the practical way to do this and to do it safely is we put the breaker in the open position, which we're in right now. So with the breaker in the open position, we're gonna start with the, we're gonna hook our hot lead from the high pot to one phase of the lines out of the breaker, or whichever one's most convenient. And then every other pole is gonna be jumpered to ground and the chassis, and that's gonna be our return on the test set. On most high pot leads, you'll see most of it is this white, or sometimes they're black, sometimes they're another color. And then you've got this part right here. So this, the white part is shielded. You've got this little gland here, it's sort of like a weather head. And then the red lead is unshielded. So this is just insulated. So we really wanna try and keep everything between here and the tip. Just consider that whole thing hot. And so we wanna hang this away from everything else that we're testing. And we've got a couple different ways we can do that. I like to hook it around something, just get it out of the way. Make sure that big bright orange cone is right in the middle of the shot. That's perfect. And then like I said, so the bottom of that pole and then the other two poles are all gonna be grounded. So everything on this, the top of B and C, and the bottom of A, B, and C are all gonna be grounded. And then when we high pot, we're checking all of the, essentially all of the current leaving the test set going to ground. That's my return value. All right, zoom out. So the controls on this guy, obviously, so per my manual, for this breaker, this is a 4160 volt breaker. It's a VR, I can give you the part number, it doesn't really matter. It's 4160 volt breaker. According to the manual, we're gonna high pot at 14 kV AC. So we set our range selector knob needs to be in the low position, which means we're going to the bottom scale on here, which maxes out at 25. We don't want the one that goes to 50, we want the one that goes to 25, so we're on low. And we're gonna go right about to just below the 15 kV AC spot. I've done this a handful of times, so I'm gonna assume this selector, I don't know if you can see the arrow on that, it's pretty small. We're gonna go to the 10 times range. So if this is, it's whatever this is times 10. So instead of being 0.2, 0.4, 0.6, 0.8, 10, or 1, it's 2, 4, 6, 8, 10. If we were in this high range on the 100 times multiplier, it would be 20 milliamps, 40 milliamps, 60, 80, and 100 milliamps, but we're not. We're on the 10 times range. I think that's where we need to be at. We're gonna be in the ground return mode because we've got everything else that we're testing, and not just the vacuum bottle, shorted to ground. So all of the current leading, essentially the way to think about this, if we're in ground mode, all of the current leaving the high voltage lead gets measured. We see that on the ammeter. If I'm in guard mode, all of the current that leaves the high voltage lead comes back on ground, gets ignored. Only the current that comes in the load return lead gets measured. I don't want that because, like I said, I've got everything grounded. If it was on guard mode, you would get pretty much nothing the way that we're configured here. So again, wobbly cam because no, no tripod today. So turn the power on, make sure your fuse is good. This external interlock is great if you're working with other people that you don't necessarily trust. You can take this out and stick it in your pocket, and it can't turn on. In this case, we're gonna leave it in. Obviously, everything's hooked up. We should be good to go. We hit the on button, and we're gonna ramp. We're gonna just slowly, gently ramp until the voltage hits about 14 on my scale. And then we're gonna read the current. We're gonna let it sit for a little bit. We're gonna read the current. Another interesting safety interlock on here, if this is in the off position and you bump the output dial up, the on switch doesn't work, which is cool. If it's set here, and it would turn on, but you pull the safety interlock, also doesn't do anything. So those are your safety things. Got to make sure everything's squared away before you get started. You should be wearing gloves. I'm not, because YOLO. So we're gonna gradually ramp. I always like to really slowly, gradually ramp it up. Hard to look at the viewfinder and do all this at the same time. So we're gonna get to about 14. So that's 14 kV AC. And as we see, nothing's happening, which is exactly what we want. Everything's really, really well insulated. Like I said, that was in the tera ohm range, so, or the hundreds of gig ohm range, so we should be all right. And we're chilling at probably about 48 milliamps, or yeah, 4.8. So we're at 0.4 on the scale times 10 on our range selector. So that's 4.8-ish, right under 5 milliamps. So we'll gradually bring that down. I like to slowly turn it off. You can just hit the off button and it grounds the output internally, but you started damaging the contacts inside the high pot. So I like to gradually bring the voltage down. Hit the off button, grounds it out, and we'll do the same on the next phases. On something bigger, or something that had a lot of capacitance, like a overhead bus duct or a large transformer or cables or anything like that, whenever you're doing an energized test, you're applying a lot of voltage to something, there's a chance that what you're testing is holding a charge, and so you always want to ground it out. This is pretty small, it's on a pallet, it's sort of isolated. I'm not super worried about it, but don't go touching it while the test set's on, because it'll light you up and it hurts. We're gonna ramp the voltage up until we get to about 14 kV. There we go, we're chilling, same exact current as last time, 4.6-ish, right around there. We slowly ramp the current back down, or slowly ramp the voltage back down. So we hit 0, hit the off button, that grounds it. We're gonna do the same thing on C phase. Just to reiterate what we're doing the line side of C phase to everything else, and that verifies, well, number one, it verifies the vacuum bottle integrity. That's the primary thing that we're doing, right? But we're also checking that it's open to everything else. All right, coming hot. We're gonna ramp up. $14 kV, there we go. And this one's right at about 5 milliamps. So we're good. That's it. That's all the tests for this. The last thing we need to do before we stick this thing back in service is put some grease on the stabs. I've already greased up the inside when they had the cover off. I'm not 100% sure if I filmed that. We're going to use the manufacturer recommends Mobile 28. This is really common stuff. You get it pretty much anywhere. Square D will sell you their own branded thing, but it's Mobile 28. So what I like to do, and hopefully you can see this all right on camera, put a glove on, just get a little bit of it, just get a whiff on there. It really doesn't need to be too much, doesn't need to be real thick. If there's grease on it already, it's really important that you clean off all the existing grease. Some greases don't play well with each other, so you need to make sure that all the existing grease is off so they don't cake together or start breaking each other down. So these have already been cleaned pretty good. We just want to make sure that when you try to rack it in, the ramps on here will allow the finger clusters to slide on and open up and clamp onto the bus instead of just like hitting and galling together or like welding themselves shut. That's no good. So we got all those on. Close this back up. I like to, any spots where I got a big clump of stuff, I'll just go back with a paper towel or a rag and just sort of get the big clumps off. Like I said, you really just need like a real light whiff of it on there. It doesn't need to be anything super crazy. It doesn't need to be really thick. And obviously you don't want it to be super gross. If you like lean on it, you don't want to have this big chunk of grease on you or make a big mess for next time. Obviously a little bit goes a long way. The less that's on there, the less like dirt and stuff is gonna cling to it over time. And that's it, gentlemen. We have tested a medium voltage vacuum circuit breaker. This 1200 amp VR, a really good example of ones that are really common in switchgear, heavy industry, even large utilities. This is gonna be very, very typical of what you're gonna see. Eaton, ABB, Siemens, they all make roughly the same thing. They look a little bit different, but the tests are all the same, the timing. Really, you just need to make sure that you're pinned out correctly. The megger, the high pot, the ductor, it's the same test everywhere you go. A couple caveats that you're gonna run into. The breakers sometimes have an internal undervoltage relay that you'll need to defeat. There's a couple ways around that. Don't be afraid of reading the manual. The manuals are intimidating, and on newer stuff, they're a lot longer. Sometimes they're harder to find, but everything you need to know is gonna be in there. The contact gap is gonna be different for every breaker. The high pot, the voltage that you need to high pot them at is gonna be different. Sometimes they'll say you can only use DC, sometimes you can only use AC, sometimes you can do both. So definitely read the manual before you get into it. Other than that, thanks for sticking around. Thanks for checking out the channel. I'm pretty new to YouTube, so a like, subscribe, even a comment. Tell me what I did right, what I did wrong, what you thought was interesting, what you thought I did that was super boring. Throw it in the comments. It really helps to grow the channel a lot. I appreciate it. Thanks for checking it out. We'll see you on the next one. Thanks, guys.